Hello and welcome to another video lesson with A.K.A. Lawson. We're still going through the introduction to AP Physics. Today we're going to start by looking at the SI system. We're going to talk about some of the standards and some of the things that relate to using the SI system, and then of course we'll do some unit conversions, often known as dimensional analysis or the factor label method. What you see in this diagram up here towards the top is the fundamental units of the SI system. Those are the key units that you must get to know or memorize. Why have units? Why is it important? Units are key to us being able to describe and explain information that we're measuring or collecting to other scientists or to other people. Units are key to being able to describe what it is you're measuring or what it is that you're trying to convey to someone else. If you go to the store and say, I want 4, for what? I'll just take 2.5 of those. 2.5 what? So everything needs a unit. Most of the time we use them without even realizing it. Of course, in science, the units tend to relate to either length or time or mass or some other physical feature, but there'll be some that'll stand out or be a little bit unusual, I'm sure. A standard is what we use to be able to relate a specific type of unit. For instance, a foot is a standard length. A meter is a standard length. It's defined very specifically, and theoretically, anybody in the universe would be able to get that same length measurement if they knew what it was based on. So standards are key to being able to have units that others understand what you mean. And of course, the SI system, I'm not even going to try and pronounce it. It does come from the French term. It's based on an international standard. It is what science across the globe has agreed would be the international standard. And you'd be surprised, there have been some major blunders in history where some scientists use inches, other scientists use centimeters, and that caused major problems. What are some of those standards? Right here in this image to the right, what you see is the standard kilogram. That ingot, that alloy of that metal, is the standard kilogram. It's got a certain mix of two different metals, and it's got a certain dimension in terms of diameter and height. And if you make that same alloy into that same cylinder with that same dimension of diameter and height, you will always have 1 kilogram of mass. When we talk about length, the meter is defined based on the speed of light. It's how far light travels in a specific amount of time. Light travels really fast, so as you can tell, that's an incredibly small amount of time that light travels 1 meter. Time is based on a transition cycle of a cesium atom. It undergoes a certain number of transmutations, and we use that to define the amount of time in 1 second. One of the things that's important about having standards and units is being able to convey them in bigger or smaller increments. If we're describing the distance between the Earth and the Moon or the Earth and the Sun, it wouldn't make sense to describe that in centimeters or meters. We need much larger units. But if we're describing the diameter of an atom or the distance between the first shell of electrons and the nucleus, then we need a really small measure of unit. And these SI prefixes allow us to move up really large numbers and down really small numbers very easily, all by factors of 10. One of the things that's important to know is there are bigger ones and there are smaller ones, but these are the ones that you'll have to be familiar with for this course. You have to know the name and the symbol. So you want to make sure that you know tera is a capital T, giga is a capital G, and so on. You'll also notice only those top 3, tera, giga, and mega, are capitalized for their symbols. The rest are lowercase. For instance, we could talk about meters, and we could talk about gigameters, kilometers, centimeters, micrometers, nanometers. Any one of those prefix versions of meters would be a bigger or smaller length than the actual meter. We could do the same thing with seconds, we could do the same thing with grams, we can do the same thing with any unit that we're using. We can make it bigger or smaller by simply adding one of these prefixes. Now, this prefix table is available on the reference table, so you won't have to necessarily memorize it, but I encourage you to. If you memorize it, it'll make conversions faster, and it'll make it so you're not flipping back and forth trying to refer back. 1 prefix unit is equal to the factor of the base unit. What does that mean? Well, when you take the prefix and put it in front of a unit, like a kilo in front of a meter, the prefix unit is kilometer, the base unit is meter. 1 kilometer is the factor for kilo, which is 10 to the 3rd meters, or 1 kilometer is 1,000 meters. That would be same thing for seconds. So 1 millisecond is the factor for milli, 10 to the negative 3rd of the base unit, seconds. 1 terabyte is the factor for tera, 10 to the 12th of the base unit, bytes. And now you can see how you can take one of any of these prefix units that you see along the left-hand column, and you get the factor, the right-hand column of the base unit. But there's another way you can also use this. That factor tells you how many of the base unit are one of the prefix unit. But we can both divide both sides by the factor, which when you divide 1 by 10 to the 12th or 10 to the 9th, all you're really doing is reversing the sign. So it turns out if we wanted to go in the opposite direction, we just reverse the sign. 1 meter is 10 to the negative third kilometers. Notice we just reversed the sign on it. 1 second would be 10 to the third milliseconds. 1 byte would be 10 to the negative 12th terabytes. So you see it's kind of easy way to be able to move back and forth depending on which one you want to do. A lot of times students use this to always put the conversion factors, the numbers in the numerator, so they're just multiplying. These systems of units, there's many of them. The one we're going to focus on is the SI system, which you saw a diagram about a little bit ago, and which is reiterated over here on the right. We're going to go over those. Those are the fundamental or the key 7 units that you'll have to memorize that all of the units are derived from. But there's other systems. There's the SI system, which is what we're going to use. The key to the SI system is it's really based on meters, kilograms, and seconds. And that's what we're going to use most often in physics is meters, kilograms, and seconds. That'll be pretty much our key units. Once in a while, we'll see some deviation from that. But most of the time, those will be the units. Other unit systems based on what you're working in. As you can imagine, a CGS system probably gives itself away. Instead of meters, it's centimeters. Instead of kilograms, it's grams. But we still use seconds. The S is the same. If we're using much smaller masses and distances, we would use grams and centimeters instead of kilograms and meters. Depends on what you're describing. And then, of course, there's the British engineering system, which is interesting because instead of using meters, we use feet. And instead of using kilograms, we use pounds. And, of course, we still use seconds. These base units that you see over here on the right in this diagram, these are the 7 fundamental units. They're the smallest number of units we need to describe all physical phenomenon that we experience. Starting from the top, moving around, we see capital K, that's for temperature or Kelvin. We see lowercase s, that's for seconds or time. We see lowercase m, that's for meters or length. We see kg for kilograms, which is a measurement or a unit for mass. We see CD, the candela, which is a measurement of luminous intensity, how bright and shining or glowing object is. We see MOL for moles, that's the amount of substance that makes it up. Have to be a little bit careful. Matter is also the amount of material that makes it up, but they're 2 different concepts. The mole and the kilogram are the amount of material, and then the mass of the material. Not exactly the same thing. So the units are related, and if you know one, you can always determine the other based on what it's made out of, or as long as you know the chemical formula and you have the periodic table, but they are technically different measurements. And then we see the capital A for the ampere, which is a measurement of current. All of these units are combined to make other units. For instance, when we talk about forces, we'll be using the units of newtons. A newton is actually a combination of kilograms, meters, and seconds in a very specific way that we'll talk about later. Speed is not on there, but speed combines 2 of those units, distance or meters and time or seconds. So speed will have units of meters for every second that it travels. And so you'll see some of these combinations, and you're probably already familiar with some of them. You just haven't really realized that they're derived units yet. All derived units are a combination of these fundamental units in some specific way. One of the things to think about units is sometimes they're referred to as dimensions. The dimensions are these fundamental units that make them up. These are the dimensions of the universe: distance, time, amount of material, brightness, temperature. Those are all the fundamental properties that we could measure of an object in the universe. Here's another table that shows those fundamental units, those 7 basic units, and again gives their quantity or what they measure, the unit or what the unit that you're most likely going to have it in, and if you get it in a different form, we'll probably be converting it into this form to be used in this class, and of course the abbreviation, the way that we abbreviate that unit so that it saves up a little space or that it makes it easier to work with. Next, we're going to work on how to convert units. Really, it's about being able to step up or down those different prefixes, being able to get to a bigger or to a smaller unit. One of the things that's key about converting to a bigger or smaller unit, you still need to be measuring the same quantity. I can convert from a smaller unit of length to a larger unit of length, but I can't convert from length to time, not unless I'm talking about a specific relationship between length and time, like speed. So it's very important to realize that most of the time, in order to convert from something like length to time, you need some kind of relationship between that ratio. Oftentimes, the simplest way to do conversions is being able to convert to a smaller or bigger unit for the same quantity, something like time. We could have seconds or milliseconds or kiloseconds or megaseconds. All those are different amounts of time. We want to convert from seconds to volume. We need some relationship between volume and seconds. The flow rate in a pipe would allow us to relate volume to time, and then we can convert volume into time or time into volume, but only if we know some type of relationship between the two. Normally, measurements of time and volume are not the same thing, and they're not the same property without some kind of key relationship between them. In order to do these conversions, we have to have a conversion factor. We have to have something that relates those two quantities. The easiest ones are, again, converting between one unit of length to another unit of length. One of the things that's not quite obvious, because when you look at these numbers, it doesn't look like you're multiplying by 1, but when you're doing a conversion, you're actually multiplying by 1. These conversion factors are equal ratios. 12 inches is exactly 1 foot. So even though 12 divided by 1 is not 1, it's 12, there are 12 inches in 1 foot. So when you're multiplying it and getting a larger number, you're actually getting the exact same length, just in inches instead of feet. 5 feet is 60 inches. They're exactly the same length, but inches are a smaller increment, so there's more of them. When we multiply by these conversion factors that you see here, you're not changing what it physically represents. You are changing the number that represents it, but it's still the exact same physical property. It's still describing the same physical dimension. Here we see an example where we could convert between centimeters and inches. There are two different ones we could use, the centimeters per inch or the inches per centimeter. There are 2.54 centimeters in 1 inch, exactly, and there are 1 inch in 2.54 centimeters. Now, why would I have two different conversion factors? Turns out, one will allow you to convert from inches to centimeters, one will allow you to convert centimeters to inches. And that's why every conversion factor actually has two uses. It allows you to convert from the numerator to the denominator and vice versa. So when you know the relationship between feet and inches, or the relationship between yards and miles, those are just relationships that allow you to convert between miles and yards or yards and miles. One of the keys to using these methods correctly is to be able to make sure that you line up your units correctly. And that's going to be important when we go through some examples in a little. Before we get into conversions, let's talk about orders of magnitude. Orders of magnitude are a nice and easy way of estimating things very quickly. Let's look at an example here. On the right, you see a diagram of One World Trade Center. And we see that it's almost 550 meters tall. Technically, it's 541 meters if you include the spire at the top of it. Then we have a dollar bill. A dollar bill has a length, width, and height dimension. The thickness or the height is the thinnest edge, and it's 0.001 meters, or 0.1 millimeters. So you could stack 10 dollar bills if they're nice and flat on top of each other, and you'd have 1 millimeter of thickness. What we're asking here is how many dollar bills would you have to stack on top of each other to equal the height of One World Trade Center? Perhaps someone would ask you, what do you think that would take approximately? Well, you could do a more detailed calculation, but you could get an idea of an order of magnitude, which is going to be plus or minus a significant figure. The trick to this, the way we get the order of magnitude, is we're going to look at the ratio of how many dollar bills would it take to fit inside of that height. Stack dollar bills next to the World Trade Center until we can see how tall it gets. Now, one of the tricks to that is saying, okay, well, what's the height? It's 541 meters, but let's make that easier on us. Let's put that in scientific notation around to one significant figure. That would be 5 times 10 to the second meters. Then let's divide that by the height of a single dollar bill, but again, put it in scientific notation to make it easier. That's 1 times 10 to the negative 4th meters. Now we can see very easily when we divide the height by the height of a single dollar bill, how many dollar bills it would fit inside of it. 5 divided by 1 is 5. Exponents, when you're dividing, you subtract the bottom number from the top. 10 to the second minus -4 is 10 to the second plus 4, or 10 to the sixth. And so what we see is it would take 5 times 10 to the sixth $1 bills to equal the height of one World Trade Center. Since 1 is a nice easy number to deal with, we could actually go out to a couple more significant figures. It's not exactly $5 million bills, it would actually be 5.4 million or $5,400,000 bills. Or, since we actually know the height out to the ones place in the meters, we would say it's $5,410,000 bills that we'd have to line up to get that height. That 10,000s place is still our estimated digit. So we could need as many or as few, we could be off by as much as $10,000 bills according to that measurement. And it's understood when we report that we have plus or minus $10,000 bills to be able to add on that extra height or to remove some of that height to be the exact same height as the One World Trade Center. The last portion of this unit is to talk about dimensional analysis. Dimensional analysis is a quick way for us to be able to convert from one unit to another as long as we have related factors. When we're doing factor label or dimensional analysis, it's all about knowing relationships. So one of them is going to be knowing the prefixes. Converting from any prefix to any other prefix is possible as long as you know those factors or as long as you have your reference table and you look at those factors. That gives you the relationships. But we could also be doing some conversions like you saw on the last slide, which are converting things like feet to miles. We'd have to know that relationship. Hopefully you had a math teacher that kind of made you memorize it. We could be converting from inches to centimeters. You'd have to know that relationship. 1 inch is 2.54 centimeters. So we need some type of reference or have memorized a lot of these conversion factors. You won't have to memorize any conversion factors for this class. Some you should be familiar with, like 5,280 feet per mile or 1,609 meters per mile. But those are things that you could look up if you have them in a homework problem. And if they're needed on an exam, it would be provided because it's understood that if you're going between any metric system and any English or other standard system, that you would need those relationships given to you in some form or another. Here we see a bunch of relationships for different lengths, different volumes. The capacity is actually, those are showing different volumes, and then different weights, which are another way of kind of measuring amount of force. When we are doing conversions, we simply have to know those relationships and then know where we're starting and where we're ending. So for instance, let's say that we have 100 yards and we want to know how many miles is equal to 100 yards, or how much of a mile is in a football field. Is a football field longer than a mile or shorter than a mile? Hopefully you know it's considerably shorter than a mile just by some general knowledge, but perhaps you didn't and you wanted to be able to confirm or show that. You always take the number that's given, in this case 100 yards, then we're going to multiply it by conversion factors, first putting in units to get us to our desired unit. Now I want yards to cancel, so I put those in the denominator. And if I look at my relationships, I can get from yards to feet. I don't have yards to miles directly, but I have yards to feet. And since I have yards to feet, that's going to be my first conversion factor. Now it would no longer have yards. I'd have the number of feet in 100 yards, which if that's what I was looking for, I'd be done. However, I'm looking for how many miles. Luckily, I have another relationship between feet and miles. I have feet in inches, so I could go from feet to inches, but then I don't have inches to miles, so that would be a long way or wouldn't get us to where we're trying to go because I'd have to convert back in some way to get to miles. But I have feet to miles like we saw in the last slide. Feet go in the denominator so they cancel, and miles in the numerator. Now, my last unit will be miles. That's the desired answer. All I have to do is put in the relationships. Well, 1 yard is 3 feet. So that means where there's the yards, I put in 1, and where there's feet, I put in 3. 1 mile is 5,280 feet. So I put 5,280 next to feet, make sure the number goes with the unit, and I put 1 mile in the numerator. Now I can see 100 times 1 times 3, 300 divided by 1 times 5,280, or 5,280, is going to be the number of miles. Now, I could compute the actual one, or I could do that kind of quick estimation we talked about. This would be 3 times 10 to the second. This would be 5 times 10 to the third. 3/5 is 0.6. 10 to the second divided by 10 to the third is 10 to the second minus 3, which is 10 to the negative 1. 0.6 times 10 to the negative 1 means that to 1 sig fig, which is what we want our answer to, that 100, those are trailing zeros, no decimal point, so they don't count, is 0.06 miles. Hopefully I did that correctly. I could check it with a calculator, but I'm pretty confident with that rapid estimation without having to check it with a calculator. Yes, students always ask, do we have to do the rapid estimation? Do we have to use the magnitude, orders of magnitude? You don't have to, but it's a good trick. A, it gets you thinking about numbers. It gets you mathematically moving, and it's great. And two, it allows you to rapidly estimate certain answers, and it gives you an advantage when it comes to time crunches or when you're trying to outcompete someone who's trying to punch in everything on the calculator. What if we want to convert between gallons and cups? We have a 5-gallon bucket, and we want to know how many cups of water will fit inside of that 5-gallon bucket. Well, we know that we have 5 gallons. And we want to know how many cups would that fit. In order to figure that out, we have to do our conversions. Now, if I look at our relationships for the volumes over here, I can get from gallons to quarts. I don't have quarts to cups. Oh, but I have quarts to pints and then pints to cups. So it'll allow me to be able to figure out how many cups there are in my gallons, going through those conversion factors based on this relationship. So you start with the number that's given, 5 gallons. Let's look at what we can convert from gallons first. We can't go from gallons to cups directly, but we can get from gallons to quarts. Now we'll be in quarts. We can't get from quarts to cups directly, but we can get from quarts to pints. Now we would be in pints, but we don't want pints, we want cups. So our final conversion is go from pints to cups. Now we see if we put in the numbers in the correct relationships, we'll have our answer in cups. The first relationship, gallons to quarts, 1 gallon, so I put 1 next to the gallon, is 4 quarts, so I put 4 next to the quarts. Quarts to pints, we see 1 quart is 2 pints, and pints to cups, we see 1 pint is 2 cups. This is a nice, easy conversion because all the denominators are 1. When you multiply 1 by 1 by 1, you get back 1. Anything divided by 1 is just the same number. So all we have to do is really multiply 5 by 4 by 2 by 2. 5 times 4 is 20. 20 times 2 is 40. 40 times 2 is 80 cups. So in our 5-gallon bucket, we have 80 cups of water.